Well, hello guys, Mr. G here, and we're going to be making another video on vertical projectile motion for the grade 12. This time we are going to be doing two questions on vertical projectile motion. Last time I said we're going to do graph of velocity versus time, but I think it's better to practice the graph of position versus time. Then next lesson, which is going to be on Monday, we'll talk about the graphs of velocity versus time. Do some questions, and then we're going to do an experiment. In that experiment, we will calculate or determine the gravitational acceleration or acceleration due to gravity, and we are going to use two different methods to do that. So please don't miss that video. That will happen next week. But now we're going to do a question on positions versus times graph. Now this question said a hot air balloon rises vertically at constant velocity. When it reaches a height of 88 meters above the ground, a stone is dropped from the balloon. A positions time graph represents the motion of the stone from the moment it is dropped from the balloon until it hits the ground. Ignore the effect of a resistance, and here is the graph, not at scale, but it will represent the motion of the object. Okay, now 1.1, taking the ground as the reference point, what is the initial position of the stone? So now what is the position of the stone here? And remember, if we take in the ground as a reference point, that means that the ground will be in the x-axis. So this one will be the 0 position. Okay, and position is a vector quantity that is going from the reference point to whatever the object is. And in this case, the object was released at 88 meters. You can see there is when the object was released. Okay, so if we draw a vector, we represent a vector, this one here will represent the initial position of that specific stone. So the initial position is going to be equal to 88 meters, but it is a vector, so we're going to write upward. So this is the first question they ask us, okay? And it's all in the graph. You don't have to do any calculation. Please note, this is very important, okay? So the taking the ground as the reference point, then the x-axis will be right on the ground, okay? And that is a vector. Now, question 1.2, how long was the stone in the air? And that refers to the total time. The total time of motion. From 0, the object starts moving up until reach the ground, which is at this point here, and the total time in motion is going to be equal to 6 seconds. You don't have to do calculation for that one either. That is the total motion, the total time the stone was in the ground. Now, next question. These first ones are quite easy. How long took the stone to reach the maximum height? So let's go there. Now, where is the maximum height here? Now, the maximum height is represented by this point here. This one here is the maximum height of the stone, or that the stone reaches. And we're going to speak quickly here. Now, why the stone? The stone was dropped. Look here. The stone was dropped from the certain height. Now, why, if the stone is dropped, move in actual fact, when you look at the graph, a little bit up instead of just being moving down? Well, there is something called inertia. As the balloon moves up, when you drop the stone will still move a little bit up. You will not be able to see it because the balloon may not be moving too fast. But the stone in actual fact move little bit up before it goes down because of inertia. It keep moving with the balloon when you drop it. So that is very, very important. So if you come here, all this, which is a curve, is when the stone is moving up before it falls. And here the stone now is falling actually from the maximum height. We'll remember up until the 88, there we go. So this one is the maximum height, guys. And if you go to the time, then it took 2 seconds to reach the maximum height. So the time to take the maximum height, I'm going to write type maximum height, was equal to 2 seconds, okay? And that is the first question without doing any calculation. Now is coming the calculation. Calculate the velocity of the hot air balloon at the instant the stone was dropped. So in other words, they ask you to calculate the velocity of the hot air balloon when the stone was dropped. Now, when the stone was dropped, the velocity of the stone was equal to the velocity of the balloon. So if we calculate the velocity of the stone, in actual fact, we are going to have the velocity of the balloon. So this one is equal to the velocity of the balloon. So this is important to know. So all we have to do is to calculate the velocity of the stone. Now, what do we have there? We have the initial position, we have the time, we have the final position, we have many data that we can use to calculate the initial velocity. All right, so I'm going to actually use the equation of motion that you can start from the beginning. And this is question 1.4. Yes, 1.4. Now let's quickly write the data. Now data, the initial position, we have it, which is equal to 88 meters. In this question, we're going to take upward as positive. It does not really matter, guys, which direction you take. We're just taking upward as positive. It's up to you. So if that upward is positive, then the initial position is positive. And note the following, something very important. We're going to look here. That is the position, but that is not the displacement. And I think this is a very good thing to point out here. The position and the displacement are not the same thing. Okay, so now I hope you will understand. I will show you now what I'm speaking about. Remember, the displacement is equal to final position minus initial position. Remember this, okay? So you can see that they are not equal, right? The initial position is 88, the final position will be 0. So now here, because the final, this is final position here, because the final position is equal to 0, the displacement will be equal to minus initial position. This is a little bit tricky. This one is a little bit tricky. So even though the initial position is upward, the displacement, is going to be from the point you're starting to the final point. This one here that I am drawing now with this other color, this one is the displacement. This one here is the displacement. All right, and I hope you look this one very carefully, because position and displacement are not the same thing. And often there is a big confusion about that. So in this case, the position, the initial position, right? Let's write both here. Initial position is positive 88, but the displacement is going to be equal to minus 88 meters. So I hope that one was clear. Okay, the time, the total time is equal to 6 seconds. And this is what we have. We also have that acceleration due to gravity is equal to 9.8 meters per second square downward, and the force is going to be negative. Okay, because everything here is downward. I think it's actually better to change the direction. So let's make the direction comfortable for us, guys. You always can do that. I told you so. So you can say it, instead of up positive, we can say down positive. Remember, we work this one by convention, but whatever is more comfortable for you. Down positive, and obviously we have to fix all the signs here. So initial position now will be a negative, and then the displacement will be positive, and the acceleration due to gravity will also be positive, right? And we are looking for the initial velocity. So if we do this, what formula can we use that we have everything? So displacement is equal to the initial velocity multiplied by the time plus half the acceleration multiplied by the time to the power 2. And here we have everything. So let's quickly substitute. Okay, and this one is the answer. Now, something important. The answer is a negative. So what does it mean? That the initial velocity was equal to 14.73 meters per second, because we say down is positive and the answer is negative, upward. So this is now the final answer for this first question. This is the final answer for this question. As I always say, you can't redo the calculation, make sure I calculated correct, but this question was quite easy. The only confusion is to understand the displacement and position. Okay, so now 1.5, which is the last question, calculate the velocity with which the stone reaches the ground. And now for this one is also quite easy, guys. So for this one, what we have, let's see, data. Okay, so what formula can you use? Very easy. Final velocity is equal to initial velocity plus acceleration multiplied by time for the total motion, for the whole motion of the object. Second note, the answer is positive because we say down is positive, meaning that the final velocity is in actual fact down. So let's write the final answer. Final velocity is equal to 44.8 meters per second. I'm going to write just down. Okay, so this is the first question. It's quite simple, but there is small tricks that you must note there, like the position and the velocity. Okay, so we're going to do another question and then we're going to stop. This one is just to recall whatever we learned last time. Okay, note this graph, but thank you. I'm going to show you now the next question. Well, guys, this is question 2. Now in question 2, they say the position time graph is given for a ball which is thrown down from a vertical height of 1.8 meters and bounces once upon reaching the ground. The contact time between the ball and the floor can be ignored. And here is the picture, the graph of the object. Something important, the ball is being thrown, so it means that the initial velocity of the object is different to zero. It's not zero because it's not been dropped, it's been thrown. It's telling you here in this part. Okay, they don't give you the initial velocity, but they say that it's been thrown. Okay, now so this is the graph of a motion downward. All right, the initial velocity in this case is not zero because the object is being thrown. And then here is the time the ball takes to reach the ground, which is 0.5. It bounces back all the way. This is the maximum height of the first bounce, and then it goes all the way to the ground away again in t time. Okay, so this is more or less the graph, and this is what we are going to be working. Thus, I calculate the initial velocity with which the ball was thrown. Now, what we have here, what data do we have? First of all, we have the initial position of the object, but we also have the displacement, and we spoke in the previous question. So when this ball is down at the bottom, this was the displacement, and I'm talking when it's before it bouncing. So this one here is the displacement, which is equal to 1.8 meters downward. Okay, we're going to select the direction just now, and by convenient, I think for the first question it's better to say downward as positive. So that is the displacement, right? And this one here is the time it takes to reach the ground. Okay, so that is important to note. So let's answer this first question quickly. This is 2.1. So what formula will be most suitable for us? And that one will be displacement equal to initial velocity multiplied by the time plus half acceleration multiplied by time squared. So let's substitute. And this is the final velocity there. Now in the question, they asked to calculate the initial velocity with which the ball was thrown. So we have to give direction. So to give the final answer correct, initial velocity is equal to 1.15 meters per second. I'm going to write down. Okay, so and this is the final answer for this first question. Quite easy. Okay, so that was question 2.1. Now, question 2.2, with what speed does the ball strike the ground? So in that case, they're asking us to calculate the final velocity of the ball. Okay, so the final velocity of the ball for the first motion of the ball before it bounces. So let's calculate that one real fast. This one is a 2.2, question 2.2. Let's write the data. Let's write what we have. Let's always do that. Okay, so this is the data. Let's see what formula we can use. And because it's a speed, you don't have to give a direction. Okay, now this is one option, this is one way. The other formula, which is really easy, and you can actually use even the other formula. Easiest one, which I didn't notice when I was doing it. You must always try to do whatever you see first. Okay, this is complicated, but look here how easy. However, I didn't notice that one when I was solving the question. Okay, now question 2.3, with what speed did the ball leave the ground after bouncing? Now after bouncing, we have this part here. What do we have? We actually have that after bouncing, when the object bounces, this is going to be the displacement of the object. This one here is going to be the displacement of the object up to the maximum height, alright? That is up to the maximum height. This one is the displacement, the new displacement of the object at the maximum height, which is equal to 0.9 meters. It's upward. So I'm not going to write the direction right now, but you can see the arrow which is pointing upward. Okay, so we have that one. We don't have the time. Okay, so be careful with this one. But we also know that at the maximum height here, at this maximum height after bouncing, the velocity there will be equal to 0. Okay, so that is all the data we need for 2.3. That is the data we need for 2.3. 2.3. So what will the first formula be for this question? Final velocity square, we have it, equal to initial velocity square, we also have it, plus 2 times the acceleration multiplied by the displacement, and we have everything. So this is the formula for us to use. I'm going to substitute.
Some kind of butterfly. Baby, you give me midnight.
Alright, and now we are going to be doing the last one. The last one is a little bit interesting, and it's a question 2.4. So this is a 2 here. Yes, you can fix it. I'm not going to be worried about that. Calculate the value of time. Now, this is quite interesting here. We have a lot of data now. It's not a big issue. We have a lot of data here. Now, we can use from starting point, from maximum height to time. For instance, we can calculate that time there, but be careful because they ask for the total time. Total time is the total time from the initial point here to the final point there. That is what they asking you, total time. Okay, the value of that t. But if we calculate this value, then we can add 0.5. Okay, but it's quite interesting because what I want to point out is that there's different ways to solve it, but I want to show you one that I found. Okay, so from here to here, the object go up and down. So when the object do the whole motion from up to down, from the starting point to the final point, the displacement there is going to be equal to 0. That is very, very important because it's starting from one point and it's ending up in the same point. The object did not have displacement there. All right, so I want to point out that, and I want to use the whole motion the whole motion from one point to another. Guys, there's other ways to do it. I am going to do it like this. You can try others and then compare your answers with mine. Okay, so I'm going to do the following. This is question 2.4 and we are going to write the data as usual. Minus because we're using down as positive because we're using down as positive. So what formula we're going to use? Now when you solve this in mathematics, you have two solutions: delta t equal to 0, which is obvious not a solution, and the other one is minus 4,2. This is mathematics, eh? That's why I wanted to use this method, because you do mathematics. Plus 4,9 delta t equal to 0. So those are the two solutions, and then you calculate for delta t. When you calculate delta t is equal to 4,2 divided by 4,9. All right, and this one is going to be giving you an answer equal to 0,857. We're going to leave it there. Now note this time is not the t they're asking you. This is the time it takes from this point here to there. So we still have to add to that time the 0,5 seconds of the graph. So the total time, which is that t in the graph, will be equal to t will be equal to 0,5 plus 0,857, and that t will be equal to 1,357 seconds. Guys, this is the end of this question. Now note the following, because I know some people are going to say, but gee whiz, Mr. G is crazy, there's very easy options to solve this question. Yes, there is very easy ways to solve the questions here, but I think you use math, so let's think, where do you use the math? So there is very easy formulas in this case. You can just divide the things in part, calculate the time to go up, then it's 2 times, and so on. It's other ways. It's other ways. In each of the questions there is many options to solve it, but this is it. So this is all for now. I hope it helped. I hope you understand. Thank you for watching. Subscribe to the channel. I'll see you next time. The next video is going to be about the graphs of a velocity versus time. We're going to understand those graphs, we're going to do the equations, and then we're going to do an experiment which is going to happen next week. Thank you for watching, guys. I'll see you next time. Mr. G here.